since I can't be there in person for lecture on Wednesday, November 19th, I'm going to go ahead and do a full lecture here on these videos, and I'm going to start out by just doing what I usually do and reviewing the material that we covered on Monday, November 17th, about acid-base stoichiometry, and then we're going to go into learning how to predict the products of precipitation reactions, and we'll see that that's even a little bit easier than for acid-base reactions. If you need some extra help, of course, we have recitation on Tuesday from 2 to 3, if you're looking at this before then. The last CSI workshop is Wednesday from 6 to 7 p.m. in Brown Building, W210. I've got extra office hours on Thursday from 10 to 12, and if you can't make it during those times, you're welcome to email me for an appointment. I don't have a lot of availability, but I'll try to accommodate you if I can. And the exam is going to be Thursday at 6:30 p.m. If you're in Section E, I'm going to go to Hill Hall 202 as usual for your exam room. And then there is homework 14 and a pre-quiz due this weekend. If you have a chance to look at them before the exam, there are a few problems at the start of homework 14 that are marked as applicable to exam 3. So it might be a good idea to look at those before you go into the exam on Thursday. So on Monday, we talked about acid-base neutralization reactions. We said that for our purposes in this class, an acid is going to be something that donates a proton in a reaction. The base is going to be the molecular ion that accepts the proton. And a neutralization reaction then is a reaction between an acid and a base that's taking the protons out of solution by reacting them with hydroxide ions. So for example, we did the reaction of nitric acid with calcium hydroxide, nitric acid, calcium hydroxide, and like any acid-base reaction with either a strong acid or a strong base, or having both of them being strong, the products are going to be water and a salt. So here we've got M being our cation and A being the anion in the salt. So over here we've got an anion of NO3, and we've got a cation of calcium 2+. So that makes the salt produced by the acid-base neutralization reaction. And for exam 3, all you need to be able to do with this is that if you're given the full equation, you need to be able to identify what's the acid and what's the base. So if I were to give you just this part of the problem and just write that out, I would say, what's the acid and what's the base in this reaction? If you were told the acid and the base, so I said you have nitric acid reacting with calcium hydroxide, you should be able to predict the products, predict that you're going to get water and calcium nitrate out of that reaction. And that's essentially all you need to be able to do with acid-base reactions for exam 3. However, in order to understand what's going on in an acid-base reaction, we need to take it a couple steps further. So first of all, remember that when we say something is a strong acid or a strong base, what we're referring to is the percent dissociation in water. So how much of that acid or base falls apart in water. It may be well under 100% that actually is going to react with water molecules. So that's what we're discussing when we say acid or base strength. How does it act in its reaction with water? Strong acids are going to be the ones that dissociate greater than 70% in water to form the hydronium ion. And so when HCl, for example, reacts with an H2O, it makes Cl minus and this H3O plus, which we call hydronium. And oftentimes to abbreviate the way that we write acid-base reactions, instead of writing that full hydronium ion, we just leave off the water and we leave this off and we write H plus instead of H3O plus. But we want to remember that the actual thing that's floating around in solution is usually not H plus, it's usually this H3O plus molecule, but it's just easier to write it as H plus. The only strong acids we're going to use, and these are listed on the equation sheet, are HCl, HBr, and HI, HClO4, HClO3, HNO3, and H2SO4. Anything that's not on that list, then we're going to assume is a weak acid. For example, hydrofluoric acid, acetic acid, or phosphoric acid are all things that don't show up on our strong acid list, so we're going to assume they're weak acids. So since we have these things that can react with water, when we start out with just this aqueous compound, we have a couple of different options for how we write it. So we could write the formula equation where we show the full compound for everything. We could write what we call the complete ionic equation, where all the strong electrolytes are going to be written as dissociated ions. So if we have a strong acid, it's going to dissociate to make H+, which is really H3O+, and A-, which is the anion that it leaves behind in water. If we have a weak acid, it's just going to stay intact when it dissolves in water. So for example, HNO3 is a strong acid. Calcium hydroxide is also a strong base, and so we're going to show them in the complete ionic equation as dissociated into their ions in solution, because that's sort of what they actually look like in solution. And then perhaps what's even more useful is if we go in and we look at which of the ions don't really do anything in the reaction, which ones just hang out. So the NO3 shows up on both sides, so we call that a spectator ion, and we say it doesn't really participate in the reaction. It has to be there for neutrality, and in order to get the protons into solution, we have to have the HNO3, but the NO3 just hangs out, and the proton really participates in the reaction. Same thing happens with the calcium 2+, doesn't really participate in the reaction. And so our net ionic equation here is just the protons and the hydroxide ions making water. And that's going to be the same for any acid-base reaction that has a strong acid and or a strong base. But then what if we have reactions that have either a weak acid or a weak base? So I asked you guys this question at the very end of class to write the balanced net ionic equation if you had the aqueous reaction of acetic acid, which is a weak acid, with calcium hydroxide, which is a strong base. What are the spectator ions? And we said the spectator ion, the only spectator ion in that equation, in that chemical reaction, is calcium 2+. So let's just go over that example in more detail. So here we've got the balanced chemical equation. We've got the reaction of acetic acid with calcium hydroxide, and when we balance it out, we have to have a 2 in front of the acetic acid in order to react with these 2 hydroxide ions. And then that gives us 2 waters, and we get calcium acetate at the end. And there's got to be 2 acetate ions for every 1 calcium, because calcium is 2+ and acetate is 1-. Okay, so again, the acetate ion is this CH3CO2-. If we write all the ions as they are in solution, well, if we're looking at the acetic acid, we said it's a weak acid, so on the left-hand side, it does not dissociate in water. It can react with a base, but it doesn't really react very much with water. So it's in the beginning, unlike nitric acid, which essentially reacted with water, the acetic acid doesn't do that. Okay, so the acetic acid just hangs out until it sees a stronger base, so until it reacts with the hydroxide ions, at which point the hydroxide pulls this hydrogen off of the acetic acid, making H2O. The acetate ion here is essentially just left behind, and again, it will interact with the calcium 2+ ion. But since the acetate ion had a different bonding structure in the beginning of the reaction than at the end, it's not a spectator ion. It's actually changing form in the chemical reaction. It started out not being an ion, and it ended up being an ion, right? So it started out as part of a molecule, and it ended up being an ion. So it's very different than what we saw with the HNO3 reaction. And then the calcium 2+ starts out as an ion, ends up as an ion, so we call that a spectator. So here's our net ionic equation. We've got the acetic acid, the hydroxide ions going to acetate ions, and water. That's our net ionic equation for that reaction. So now let's discuss some new material, things that we didn't talk about on Monday in class. So all the acids we've seen so far have been what we call monoprotic acids. That means when you put them in water, you get 1 H+. You put HCl in water, it goes to H+ plus Cl-, right? But we have acids as well that make more than 1 proton in water. So for example, we have diprotic acids, something like H2SO4. If I put that into water, I'm going to get H2SO4 aqueous. In the abbreviated form, we can write this that it makes H+ aqueous. We know, of course, that's really hydronium, H3O+. plus an HSO4 minus ion, the hydrogen sulfate ion, and then that hydrogen sulfate ion can go on to also lose its proton. It's actually an acid as well. H2SO4 ends up being a strong acid, so this first proton dissociates almost 100%. This second reaction doesn't actually go quite to 100%, so I'm going to start doing something that we're going to do a lot more of in Chem 2, which is draw this double-sided arrow, just meaning that some of this is going to go forward, but a lot of it's going to stay as HSO4 minus. So we would end up with an H plus the sulfate ion, SO4 2 minus aqueous. And then if we were to write the overall reaction, going all the way from start to finish, it would be H2SO4 aqueous going to 2H plus aqueous plus SO4 2 minus aqueous. So that's what we mean when we say we have a diprotic acid. But we can also have triprotic acids. Phosphoric acid is the only triprotic acid we're really going to run into. And just like we saw for the sulfuric acid, the phosphoric acid, the overall reaction would make 3 protons plus the phosphate ion, PO4 3 minus aqueous. Okay, when it reacts all the way in dissociating in water. And if it were to react with a base, because this reaction, again, it's not in water, it's not really going to go all the way to making those 3 protons. Quite a bit of it is going to hang out as H2PO4 minus or HPO4 2 minus in solution. But if it were to react with a base, all 3 of the protons could easily be pulled off by a hydroxide ion. So for example, we could look at the reaction of our phosphoric acid H3PO4 aqueous with calcium hydroxide, so just sticking with the same base that we've been looking at so far, CaOH2 aqueous. And I didn't really leave enough room to balance here, so let me go back and see if I can make just a little bit more space, because we're going to write the unbalanced equation first, and then we're going to have to balance it out. So that plus calcium hydroxide going to, what are our products going to be? Well, we're going to have water, of course, always, so liquid water, plus our salt, which in this case is going to be calcium phosphate, right? So we've got the phosphate ion and the calcium ion, and the phosphate is a 3 minus, and the calcium is a 2 plus. So if we swap the charges for the subscripts, we know they're going to have 3 calciums to offset that 3 minus times 2 phosphates to counteract that 2 plus. Now, interestingly, calcium phosphate, once we learn a little bit more about solubility, that is not a soluble compound, so it ends up actually precipitating out of solution. So this is an acid-base reaction, but it actually makes a solid, so you could consider it to be an acid-base and precipitation reaction at the same time. So let's try and balance this out. So let's just do this in a systematic way. Let's look at our hydrogens, our phosphorus, our oxygen, and our calcium. So if I look at my hydrogens, I've got them in both my phosphoric acid and my calcium hydroxide. And actually, you know what I think I'm going to do is I'm going to start with the calciums in this one, because the calciums, I've got 3 on this side and 1 on that side. So why don't I try just putting a 3 here, and that's going to adjust my oxygens and my hydrogens as well. So that might be a really good place to start. So now I've got 3 calciums on both sides. Let's go up through this list. Let's look at the oxygens next. Oh, and another easy thing we can do even before we do that, let's just look at the full phosphate ion. So we've got 2 phosphate ions over here, and if we put a 2 here on the left-hand side, which I kind of didn't leave room for, so that 2 goes right there, we get 2 phosphates on the left-hand side. So now we've got the same number of phosphates on both sides and the same number of calciums on both sides. Now let's add up the oxygens and hydrogens, which are going to be a little more challenging. So we've got 2 times 4 oxygens in that compound, so that's 8, plus we've got 3 times 2 oxygens in this calcium hydroxide, so that's 6, so we get 14 oxygens on the left. We've got 1 here in the H2O liquid, and we've got 8 over here in the calcium phosphate. So if we've got 8 there, we need 6 more. So if we put a 6 in front of the H2O, that gives us the 6 oxygens there. So now we've got 14 on both sides. The phosphorus, we've got 2 over here on the left. We've got 2 over here on the right, so we're doing fine there. And now let's see if our hydrogens are balanced. So we've got 2 times 3 hydrogens over on the left, so 6 from the calcium hydroxide. We've got 6 from the phosphoric acid, so we've got 12 on the left. We've got 6 times 2, or 12, on the right. So we're balanced out. So we know this is a balanced chemical reaction, and this is what we would see if we reacted phosphoric acid with calcium hydroxide. So I've been using these acid names from time to time, but in order to make sure that everyone's on the same page with those, let's go over briefly the rules that we use for systematically naming acids. Most of the acids we're going to be seeing are what we call oxoacids. They have oxygen in them. So let's start with those, and those also are the slightly more complex ones to name. So if you have an oxoanion, so we've got something like PO4 3-, you're going to take its name, the phosphate ion. If it ends with ATE, so phosphate, we're going to replace that with IC. So it's going to be phosphoric acid, H3PO4. For another example, if we have HClO3, well, the ion involved in that is the chlorate ion, so you've got to know those oxoanions first, so that becomes chloric acid. 8 goes to ic. If we have something that ends with ITE, if we have something that ends with ITE, so for example, if we have the hypochlorite ion, ClO-, if we add a hydrogen to that, we get hypochlorous acid. Okay, so the hypo was already part of the ion name, hypochlorite, and then we make it into hypochlorous acid because it ends with ITE in the original name. As you work on memorizing these, I went ahead and summarized in this table all the oxoacids and the oxoanion names that we learned already that go along with them. So you can use that as you try to remember what each of these names is. And like I said, not everything has an oxoanion in it, so sometimes we have things that don't contain oxygen. And so in that case, we always are just ending our ion name in IDE, so Cn- is cyanide, Cl- is chloride, I- is iodide, right? And so if we add a hydrogen to that, we just put hydro at the front, so cyanide becomes hydrocyan, and then we had IC, an acid at the end, so cyanic acid, and Cl- becomes hydrochloric acid. So practice with that so that you become comfortable writing formulas from names or names from formulas for acids, and I'll expect you guys to know all of those names, oxoanions, and all of the other acids as well. So we've talked extensively about acids. Let's take a minute and talk about bases. Strong bases are the ones that are going to dissociate to make hydroxide ions in H2O. So let's start talking about strong bases. So we've looked at calcium hydroxide, so CaOH2. And if you put that in water, it dissociates to make calcium 2+, aqueous and 2 OH minus aqueous, right? So that's a strong base. We also can have, NaOH. That's a strong base. And that's going to, of course, make the sodium plus ion and an OH minus. I'm actually going to modify this and put, instead of all, let's put most. I realize that in Chem 1, I put this because the only strong bases we're going to see in Chem 1 are soluble hydroxides. But in Chem 2, we are actually going to look at some other types of compounds that act as strong bases. So again, in Chem 1, we're going to see all of our strong bases being soluble hydroxides, but later on we'll see some others. So just as a point of interest, calcium oxide, if you put that in water, and in this case we've got to show the water to show what happens, you get calcium 2+ aqueous, and you also get 2 OH minus ions from the reaction of this oxide with the water molecules. So a very strong reaction there. And so that's another strong base, but we won't really use that in Chem 1. We'll talk about it more in Chem 2. So what about weak bases? Weak bases are what we'd call weak electrolytes, so they dissociate much less than 70% in aqueous solution. So KOH is a strong base, dissociates into potassium plus and OH minus in solution. And I apologize that my handwriting here has gotten really sloppy. My stylus broke, so now I have to use my finger. I'm not as good with my fingertip as with the stylus on this screen. So then we've got a weak base NH3, and then that is the only weak base we're going to see in Chem 1, and so that's ammonia, of course. And if you put ammonia in water, what happens? Well, like I said with the calcium oxide, we've got to include the water now to show what's going on, because if it's a weak base, it's going to accept a proton, and it's going to accept it from water just a little bit. So again, I'm going to use that double-sided arrow to show that this only happens a little bit in water. So you would get a little bit of NH4 plus aqueous, and of course that would leave behind a little bit of OH minus, so it's going to increase the amount of OH minus in solution. But more interestingly then is to look at the reactions of weak bases and weak acids with other acids and bases. So let's take a look at all of the different possible types of acid-base reactions we might see. So let's start with the ones that we've seen before. Strong acid, strong base. So if we had, for example, nitric acid and calcium hydroxide, we've got a strong acid. That's on our strong acid lists. Calcium hydroxide is a soluble oxide, and so we know that it's a strong base, and that goes completely to water and calcium nitrate. So any strong acid, strong base is going to go completely to water and a salt. So our next type of reaction, and we've looked at one of these as well, a weak acid, strong base reaction. We looked at, instead of hydrofluoric acid, we looked at acetic acid, but they're both weak acids. And because calcium hydroxide is strong, it's still going to react completely with the HF. So it's still going to go all the way to water. That shouldn't be aqueous, it should be liquid. And a salt. Okay, so exact same thing. Weak acid, strong base makes water and a salt. And luckily we have the same sort of simple type of reaction for a strong acid with a weak base. The thing is going to go all the way to completion. So in this case we've got HNO3, that's our strong acid. Our weak base is NH3. In this case, the NH3 is going to take that proton and become NH4+. So we've got our salt, but it doesn't make any extra water. There's nothing there to make extra water with because there's no extra hydroxide going on, around. So we get just our salt out of this. So very simple, but we're missing the extra water. That doesn't make the extra water. And like I said, NH3 is the only weak base we're going to see in Chem 1. And so put any strong acid with NH3 and you're going to get the ammonium cation, NH4+, with some sort of an anion. Those are the only reactions we're going to see in Chem 1 in general. In Chem 2, however, we're going to also look at weak acid, weak base reactions. These are more complicated because they don't react all the way. They're often much less than 100% reacted, whereas if we looked at our reactions up above here, they go all the way to completion, meaning all of the limiting reactant gets used up. That's not the case here. Even if we've got a limiting reactant, it might not even get all the way used up because it's just that this proton doesn't want to leave enough and this guy doesn't want to pull it enough, so all of the reaction doesn't actually go to products. But it's very much the similar case as we had for our strong acid, weak base. We have our weak acid, weak base, and we make a salt. Again, we won't really look at these in detail till Chem 2 because they're more complex. So with that, I'm going to end this video, this first video. That was a lot of review and hopefully some more insight into acid-base reactions. In the next video, we're going to talk a little bit more generally about electrolytes and about precipitation reactions.